Hello, my name is Alex Donner. Thank you. I'm a second-year graduate student. I'm studying here at the University of Colorado at Boulder at the Impact Institute with Mihai Harani. And today I'm going to be talking about the Lunar Meteoroid Monitor instrument that we're developing. Thankfully, you've all been constantly bombarded with information and talks about the volatiles on the lunar surface and permanently shadowed regions, so I don't have to belabor you with that anymore. So the goal of this instrument in particular is to measure the dust flux bombarding the lunar surface and sort of help quantify how that might be affecting the volatile transport and losses across the lunar surface and in these permanently shadowed regions, as well as just the dust ejecta in general and the lunar exosphere. So there was an instrument in the past that attempted to do this aboard Apollo 17 called the Lunar Ejecta and Meteorites Experiment, or LEAM. And that did a couple of things very well, but a couple of things wrong that we're hoping to address with this new instrument. It had three different detectors. One was parallel to the lunar surface and two were perpendicular to it. The parallel one was the one that was intended to measure those impactors, and the two perpendicular ones were hoping to measure the actual ejecta cloud from nearby impactors. But it was so sensitive that it was actually predominantly measuring dust, highly charged dust that was lofted via other mechanisms like UV and solar charging. So our new instrument won't be so sensitive to those things, and we'll be able to distinguish from impactors, interplanetary dust flux that's impacting it. The other problem that this LEAM instrument had was it couldn't withstand the temperatures that we see on certain regions of the moon, that upwards of 120 degrees Celsius. So we hope to address that with our new instrument as well. To further motivate this new instrument, we're hoping to be able to address some of the goals in the Artemis Science Definition Report, to be able to study and assess effects on materials of long duration exposures to the lunar environment, particularly this micrometeoroid bombardment, and to monitor real-time environmental variables affecting safe operations, which includes monitoring for meteors, micrometeors, and other space debris. I'm looking forward to one of the posters on how we have to be able to get these small dust particles off of other things, because this dust can be dangerous. So to help motivate the science goals for this particular instrument, we're going to look at a Grun et al. Paper and a Picorni et al. Paper. On the left is a plot from this Grun et al. Paper on cumulative dust flux around 1 AU from other spacecraft in this sort of best fit line. And I'm going to use 3 micron diameter dust particles as sort of a reference line for the rest of this presentation. And so this orange line on this plot represents the cumulative flux for 3 micron diameter dust particles and larger. And it says that we should expect roughly 20 particle impacts per week per square meter. So we're going to use that as a constraint for our design. And then on the right, we have the Picorni et al. Plot, which shows the speed or the speed distribution independent of particle size of meteoroids that we expect to be bombarding the lunar surface. This is also compared to Earth. It kind of shows you how much gravitational focusing affects it. But the key takeaway from this one that we use as a design constraint is that we expect a majority of these impactors to be going at least 10 kilometers per second. And so using those design constraints, we want our detector to be able to get 10 fully characterized meteoroid hits per week. And so we have a design area of half a square meter with a mass and velocity threshold of a 3 micron diameter particle going roughly 10 kilometers per second. So all in all, our instrument design we need to have a 100% duty cycle, so it's not turning off throughout the lunar day. LEAM, for example, was turned off for about 8 Earth days at a time during that lunar noon period, which was about a 75% duty cycle. And we want this full field of view of 1.5 pi stridians, or like the 60-degree cone. We want to be able to get the mass of the impacting meteoroids within a factor of 2 uncertainty, and the impacting velocity within 10% from 3 to that top end of expected speeds of 70 kilometers per second. And so this principle of operation to this instrument is actually very similar to LEAM. LEAM used 2 thin metal films, and then measured the impact ionization plasma. Here, we're switching away from measuring the plasma, and we're using a permanently polarized capacitive plastic sensor that is, in this case, made of polyvinylidene fluoride, or what I'll call PVDF. And what's neat about PVDF is the signal produced after the electronics amplitude is proportional to the mass of those impactors and the velocity to a power, usually about 2.5 to 3, depending on the specific film. And so if we can use these 2 thin films to measure the time between impacts to get our velocity, and then we can get the mass of the particle from the peak. So this lets us fully characterize those dust impacts. And then we do have to account for the energy lost by penetrating that first thin film. So on the left here is the momentum threshold for a particle to penetrate through that first thin film. The thin diagonal black line there is PVDF by itself. We intend that first film to be roughly 6 microns thick. The green line shows the addition of this 1.5 micron coating of silicon dioxide, and this is to help reflect that extra infrared away to keep the heat down. So any velocity mass above that green line is particles that should penetrate through that thin surface. And the overlaid on this is the speed distribution of the expected impactors, showing that we should see penetrating through that first film the majority of dust impactors on the lunar surface. In addition, the orange box indicates the expected size and speed range of beta meteoroids as well. And so this does show that we do expect to be able to fully characterize some of those, which is very, very nice. And then the ratio of the speed of particle encounters on the second PVDF is plotted here on the right. And this lets us account for that energy loss and still get a fully characterized impactor, from initial velocity to energy loss to the mass of that impactor. For reference, those thin blue lines on both plots indicates that 3 micron radius for a typical interplanetary dust particle. And so here I have sort of our prototype so far. On the left is what it might look like deployed on the lunar surface with the shielding and thermal blankets, and the actual instrument displayed or deployed. On the right, you can see inside of those blankets and what it might look like in a stowed sort of launch configuration. We currently have this fan-like design because it allows for a very small, compact launch configuration, but a very nice, large deployed area. So we can sort of supersede and do better than what we did with LEAM. And so overall quick summary of sort of the features of this instrument is that deployable structure for this very large active area with compact configuration for launch stowing. A low power electronics, and this is something I didn't mention before, but what LEAM did well was it had a low power electronics, so it was able to operate throughout the entire lunar night, even though it couldn't operate through the entire lunar day. And this is how we can get to that 100% duty cycle. And then that thermal design to enable continuous operation with temperatures at 120 degrees Celsius. And overall, this instrument is designed, envisioned to be part of the Payload series for Lunar Environmental Monitoring Stations, or LEMS, deployed on the lunar station with this items program, hopefully with lifespans of over 2 years. And that's all I have. Any questions?
Okay, if you have a minute or 2 questions, anybody in the room? Yeah, I guess if you could just approach the microphone in the aisle.
Hi, I'm just wondering if you've envisioned how you would do the deployment. Do you have a ConOps for robotic deployment, or do you require astronaut deployment, or have you thought about that?
The beauty of that simple fan design is it could be a very simple robotic deployment, sort of aboard a lander, a simple, not solenoid, servo could open that fan all the way. It shouldn't be a very difficult deployment at all.
I actually have a question about your PVDF sensor. Are you worried at all about thermal aging of the microstructure as you get exposed to these higher temperatures, throwing off your calibration?
So this is something that my current PhD research is focusing on heavily, actually. And I'm going through a series of testing on the typical PVDF monitor as it is now, and how that calibration might age with high temperature exposures. Currently, we haven't seen any signs that once it's exposed to a temperature, the calibration should continue to decay. It seems to decay to one set point and sit there. But we are continuing to test that, and we have other different PVDF copolymers as well that might show stronger thermal resistances that we're testing in the near future as well. So,
Any other questions? I'll ask one. So what would you say is the TRL of the entire system, or?
Currently, I believe it's sitting around
components?
3 or 4, and we're hoping to get it to 6 within the next 3 years or so, if I understand correctly.
Okay, very good. That just about takes us to our next speaker. So thank you, Alex.
Thank you.